All right, so we've just learned about these formation reactions, writing or showing how any compound could be made directly from its elemental components. And now we're ready to put those into the context of Hess's law, which we just learned about a couple of segments ago, showing that we can add together different reactions to find the energy change of some larger reaction. Right? So when we go to use formation reactions to do that, to find the enthalpy change of some other reactions, here are the sort of the 3 steps that I'd recommend you follow. First, you want to write the formation reaction. Formation reaction, showing the making of that compound for each species. Next, you would combine the reactions using Hess's law, accounting for their directions and or coefficients. So maybe you need to reverse a reaction like we had done in the previous example. Maybe you need to double a reaction, have it happen twice like we had in the previous example. Okay? Keeping in mind that whatever you do to the reaction, you must also do to its corresponding energy. So if you change a reaction's direction, don't forget to change its enthalpy by multiplying by a -1. And if you use a reaction multiple times, 2, 3, 4 times, because it has a coefficient in the overall reaction of 2, 3, or 4, you also must multiply the enthalpy of formation by that same coefficient. Once you've done that, you should be able to just add up the parts, and the reactions will work out, as will the energies. And so when you add the now modified formation values, taking into account these changes here, you will get the delta H of reaction. So I've set up an example for us to see it at work. Let's find the enthalpy of reaction. It'll be the standard one. I put the little standard symbol there because we're going to use standard enthalpy of formation. So that's just a little semantic issue, but we are going to use standard formation values, therefore we're finding this, quote, standard enthalpy of reaction. For the decomposition of magnesium carbonate into magnesium oxide and carbon dioxide. So step 1, write a formation reaction. And that's what I've done right here. To make MgCO3, we need magnesium, carbon, 3/2 of an oxygen. I went to Appendix 2b, found that its formation value is -1111.69 kilojoules per mole. MgO, formation from magnesium and 1/2 mole of oxygen. Enthalpy of formation, -601.24. And we already saw carbon dioxide earlier. So these now become the reactions that we can try to add together to get this overall reaction here. We didn't have to have somebody else give us those reactions like I did earlier with the imaginary A, B's, and C's. Okay? But now it becomes, how do we get these to give us this overall reaction? And it's pretty straightforward. Because we're always writing formation reactions, any compound that is a reactant is going to need to be reversed. So in the sort of the summing part over here, the MgCO3 is going to need to come apart to give us the Mg, the C, and the 3/2 O2. You see, this coming apart is going to give us some of the building blocks for these other reactions down here. But because we reversed the reaction direction, the delta H is now -1 times the -1111.69 kilojoules. Any chemical that's a product, we would be forming it. So we're going to use its formation reaction in the correct order. The only issue would be whether or not we have a coefficient. And for both MgO and CO2, we don't. So their enthalpies of formation are really unaffected in this setup here. And so for the C, I'm going to write it C plus O2 to give us CO2. Delta H equals -393.51. So if you've set up your formation reactions correctly, when you then go to add them together, you'll get cancellation. For example, my carbon from my carbon dioxide reaction cancels with the carbon from the magnesium carbonate reaction. My magnesium from the MgO reaction cancels with the magnesium from the MgCO3 reaction. And this total amount of oxygen. It's in two different parts, but that's 1.5 moles of oxygen canceling with 1.5 moles of oxygen. So what's left? MgCO3 decomposing to MgO plus CO2. Sorry, that's down at the bottom of the board. I hope you can still see that though. It is in fact our target reaction. Therefore, we can just add up our energies over here, taking into account this negative sign that we had to use on our first reaction. And so the enthalpy of reaction, standard enthalpy change of reaction, is positive 116.94 kilojoules. So we were able to determine that. Now, if we do this process enough, we realize that we're always doing the same thing, okay? We are always going to end up reversing the direction of our reactant reactions, keeping the same direction of our product reactions. So the result is going to be that we're always multiplying our reactant formation values by a negative number. And then we're adding those together. Think about what I just said. Multiplying something by -1 and adding it together with something else. That's exactly the same thing as just subtracting, right? Taking these values as is and subtracting them from the other values. Now we'd have to account for coefficients, which I don't have in this example, but I will in the next. All right? But in short, what we're going to do, if we want to cut out all of this work of actually writing all the reactions and just paying attention to the pattern that plays itself out with the energy changes, it ends up being this: sum up. That's a Greek letter sigma, meaning to sum up or add up all of the enthalpies of formation of your products. And you add up the products first, taking into account their coefficients. That's what the N represents, the coefficients. You add them first because their signs don't get changed. And then subtract the sum of the enthalpies of formation of all of your reactants. Keeping in mind, again, the coefficients. And subtracting them, that's the same thing that I was just saying a second ago. Multiplying by -1 and adding is the same thing as subtracting. So what we really did for this reaction, while we still have it here, is we really took the sum of our product values, -601.24 plus -393.51, minus our reactant values, -1111.69. And you see this minus is just like multiplying by the -1, and that's how we got the positive 116.94 kilojoules as the enthalpy change of this reaction. So this equation at the top of our board is the mathematical expression of Hess's law of heat summation. And it's a powerful shortcut, really, that you have permission to use now in order to find the enthalpy changes of reactions. Now pause right here and I'll get one more example set up that has some coefficients, and then that's going to round out our chapter 6 for us.